Mercury, small, scorched, and long overshadowed by its planetary siblings, was for decades considered geologically simple and unremarkable. As the closest planet to the Sun, it was assumed to be a barren world, scorched by relentless solar radiation and stripped of anything interesting. But this perception changed drastically with the arrival of NASA's Mariner 10 mission in 1974. Although the spacecraft only imaged about 45% of Mercury's surface, what it revealed was startling. A heavily cratered, ancient world resembling the Moon, but with key differences that hinted at a much more complex history. Then came Messenger, a groundbreaking mission that orbited Mercury from 2011 to 2015. Thanks to its sophisticated imaging tools and spectrometers, scientists were able to map nearly the entire surface of Mercury, uncovering secrets hidden for billions of years. For the first time, the planet's terrain was seen in detail, exposing countless craters, mysterious smooth plains, and massive fault scarps, clues to a violent and dynamic past. Among Mercury's many features, one stands out for its sheer scale: the Colonization Basin. This immense impact crater measures over 1,500 kilometers across and was likely formed around 3.9 billion years ago during a period known as the Late Heavy Bombardment. The energy released in the collision that created Colonization was so powerful that it didn't just reshape the local surface, it rippled through the entire planet. On the opposite side of Mercury, in what scientists call the antipode of the Colonization Basin, lies a bizarre region known as the Weird Terrain. This jumbled and chaotic landscape is believed to have formed as a result of shock waves converging on the opposite side of the planet from the impact. But impact craters were only the beginning. Messenger revealed something no one had expected. Despite its proximity to the Sun, Mercury appears to have water ice in permanently shadowed craters near its poles. These regions never see direct sunlight due to Mercury's almost non-existent axial tilt. Combined with the lack of atmosphere, these deep polar pockets remain cold enough to preserve ice for potentially millions of years, just meters away from areas experiencing extreme solar heat. Even more surprising was the planet's composition. Conventional models predicted that Mercury, being so close to the Sun, would be depleted of volatile elements like potassium and sulfur. But Messenger detected these elements in unexpectedly high concentrations. In fact, potassium on Mercury exists at levels 10 times higher than on the Moon or Earth. This posed a major puzzle. These elements should have been vaporized in the early high-temperature environment near the Sun. Their presence suggested that Mercury either formed elsewhere in the solar system or that our understanding of planetary formation was incomplete. This led to a dramatic reconsideration of Mercury's origin. Rather than forming in its current location, some models now suggest that Mercury was born much farther from the Sun, perhaps even beyond the orbit of Venus or Earth. At that greater distance, it would have been easier for volatile elements to become incorporated into its formation. Later, due to gravitational interactions with other planets, especially the mighty Jupiter, Mercury may have been flung inward toward the Sun in a chaotic reshuffling of the early solar system. Such a journey would explain not only its current position, but also its high density. Mercury has the largest core relative to its size of any planet in the solar system. About 75% of its radius is molten metal. This core generates a magnetic field, something unexpected in such a small planet, and evidence that Mercury is still geologically active beneath its surface. At infinity beyond, this planetary enigma serves as a prime example of how initial assumptions can be shattered by data. From mysterious ice near the Sun to a massive iron core and a complex, volatile history, Mercury has gone from a planetary afterthought to one of the most compelling objects in the inner solar system. As scientists from infinity beyond and around the world continued to analyze the wealth of data returned by Messenger, Mercury's status as a planetary mystery only deepened. One of the most striking findings was just how dense the planet truly is. Mercury is the densest planet in the solar system, even denser than Earth when corrected for gravitational compression. This extreme density is due to its enormous metallic core, which occupies around 75% of the planet's entire radius and nearly half of its mass. This raised yet another intriguing question. Why does Mercury have such a disproportionately large core? The answer may lie in one of the most violent episodes in its history, a cataclysmic collision in the early solar system. According to a leading theory, young Mercury may have been involved in a massive planetary impact with another embryonic world. This impact was so extreme that much of Mercury's outer silicate crust and mantle were blasted into space, leaving behind a stripped-down, core-heavy world. Evidence supporting this theory comes from Mercury's heavily cratered and chemically distinct surface, as well as its lopsided magnetic field. Unlike Earth's magnetic field, which is fairly symmetrical, Mercury's magnetic field is offset significantly toward the north. This suggests unusual dynamics within the planet's interior and provides further clues to the planet's tumultuous past. The aftermath of that colossal impact might have also altered Mercury's orbital path. Today, Mercury follows the most eccentric orbit of any planet in the solar system. It swings dramatically between its closest and farthest points from the Sun, something that would be consistent with a world thrown off course by a massive gravitational event. This elliptical orbit contributes to Mercury's extreme temperature variations, with daytime highs soaring above 430 degrees and nighttime lows plummeting to 180 degrees. Even more puzzling was the fact that Mercury, despite its proximity to the Sun and apparent lack of geological activity on the surface, still maintains a magnetic field. This means the core is at least partially molten and capable of generating a dynamo effect, much like Earth's. The expectation for such a small planet was that it would have cooled and solidified billions of years ago, losing the internal heat necessary for such magnetic activity. But MESSENGER's data proved otherwise. Mercury's internal engine is still running. A new model for Mercury's internal structure began to take shape. Scientists propose that the planet consists of a solid silicate crust and mantle, beneath which lies a solid shell of iron sulfide. This layer surrounds a liquid outer core and potentially a solid inner core at the planet's center. Such complexity was wholly unexpected and challenged every existing model of planetary formation in the early solar system. The implications were profound. The idea that planets could form with such diversity, and that their destinies could be so drastically shaped by early impacts and migrations, revolutionized our understanding of planetary evolution. Mercury's story suggested that even small, seemingly barren planets could have rich, dynamic histories. Beyond the planet itself, the story of Mercury tells us something larger about the nature of the solar system. It is not the stable, clockwork-like system we once believed. Instead, it is a chaotic environment where gravitational interactions between planets can shift entire orbits, cause collisions, and alter planetary destinies. Mercury, flung inwards and stripped of its outer layers, stands as the starkest example of this cosmic turbulence. Today, thanks to missions like MESSENGER and the interpretations made possible by teams like those at Infinity Beyond, Mercury is no longer dismissed as a lifeless rock too close to the Sun to matter. It has emerged as one of the most compelling windows into the violent, unpredictable, and awe-inspiring history of our solar system's formative years.